Hello everyone, Professor Dustin here, and this video is going to be a solution to this whiteboard problem called Seesaw. So in this problem we have a board with two different lengths on it because it's being balanced on a point right here, so we know the length on one side is 37.5 centimeters, we know the length on the other side is 113 centimeters. There's also two additional masses hanging off the end. M1 is 15, and we want to know for part A, what M2 should be so that this board is balanced. Notice that the board itself is massless, so the only forces we're going to have on this problem are the forces from M1 and M2, but of course the pivot point is acting at the center of the board. So I'm going to start this problem by getting a nice free body diagram of that board. So keep in mind that this free body diagram is going to have actual locations of the forces on it rather than just starting at the center of mass. That's because this is an equilibrium problem where the board is also not rotating, and so we need to keep track of where those forces are actually acting. So I'm going to start by just putting the force of the pivot right there, and I guess I'll call that FP. And then we've got the two forces on the other side. I could write them F1 and F2, but they're really just going to be gravitational forces, so I'm just going to write FG1 and FG2. Just don't get confused. Those are the gravitational forces associated with each mass, M1 and M2. And really there should be like a connecting force, like a tension force downwards, and then an FG1 here, and then a tension force upwards or something, but we can just replace those with, we know the tension forces will be the same as the gravitational forces, so this is just conceptually simpler. Okay, and so we might think, oh, this is a Newton's second law problem, a static problem, so let's start by summing up the forces on this object, Fx and Fy. So that's going to be pretty easy because there's no forces in the x direction, and the y direction has an upwards force Fp, and then some downwards forces, which is going to be m1g minus m2g. And this thing is going to be in static equilibrium, so we would think, okay, great, set that equal to 0, and solve. The problem is that we have only one equation because the x direction is not going to help us, and we have too many unknowns. We don't know what the pivot force is doing. We rarely know what the pivot force is doing from the outset. And in this problem, we are actually looking for M2, so we have another unknown. So we're not going to be able to use Newton's second law in a linear fashion by summing up all the forces to find the mass. But we could use the torque equation. We now have a third equation which says that this thing is, not only is it in static equilibrium from linear motion, it's also in equilibrium for rotational motion. So we also have the sum of all the torques are going to be 0. There's going to be 3 torques, right? Torque from 1, the mass 1, torque from mass 2, and then a torque from the pivot. And those should add up to be 0 if this thing is going to be in rotational equilibrium. So to go into a bit more detail, I'm going to write out each one of these torques using the torque formula Rf sine phi. So there's them writing out, in sort of naive physics fashion, I'm going to apply the Rf sine phi formula. I'm going to apply it for each situation, so I'm just writing down the formula and just changing the indices. This is going to help me think about what the best thing to do next is. Because the next thing I need to do is I need to decide where the origin of the coordinate system is, so I know where to calculate the torques about. I have to pick the same origin for all 3. Now, normally, and this is the best advice that I'm going to use now, is that I want to pick the coordinate system about the point of rotation, to be 0 about the point of rotation. So the reason that's a nice thing to do is because we don't know anything about Fp. Okay, we have another equation, so it is possible that in this situation we could, pick a random point somewhere else. We would have Fp as an unknown, and then we could use the Newton's second law to solve for Fp, but let's not do that. Let's do the simplest thing, which is let's pick an origin which makes Fp vanish. And the way we do that is we pick it so that Rp is equal to 0. That means that we're going to calculate the torques about the point of rotation. So the distance between the point of rotation and where that force is being applied is 0, and the whole thing is 0. So that's definitely the easiest thing to do in this situation. For the other two, I'm just going to enter the values which we know. The distance from the point of rotation to the first one is d1, and that is going to be m1g for the force. And then sine of phi 1, well, that has to be the sine between the r vector, which is right there, r1, and fg1, but that's going to be 90 degrees. We can see if we pull that out and make sure they're tail to tail, we're going to get 90 degrees there. Sine to 90 is 1, and so I don't need to fill anything else in. I'm going to have to make the same argument over here. Here's R2. Again, I really should pull this thing over here to make sure that it's clearly tail to tail, but again, that's going to be 90 degrees as well. So for the second force, the second torque, it's also going to be relatively easy. D2, that's the distance from the pivot to the second one. M2 times G, sine of 90 is 1. So I did something kind of careless here. I should have been a little bit more careful and said this is torque in the z direction, and so each one of these individual torques is also in the z direction. Over here, I'm not doing that. Over here, I'm actually calculating the magnitudes of the torques, but when I put the magnitudes into a component form of the sum of the torques, I need to put in the negative signs, right? And so I'm going to have something like d1 m1g plus or minus d2 m2g equals 0. To determine the plus or minuses, I need to do the right-hand rule. Now, there's only two terms, so it doesn't really matter as long as I'm consistent, but let me do the right-hand rule carefully. Of course, I can't really show you the right-hand rule, so I'm just going to talk myself through it. If I try to do the right-hand rule here with R1 and FG1, take my right hand, point it in terms of R1, I can see that I don't have to move my hand. My thumb points out of the page, and so that means that this guy is the positive one. If I do the other thing, I can't use my right hand to point in the direction of R2 and FG2 and then cross into FG2 unless I flip my hand over, so that's going to be the minus 1. This equation has only one unknown, and that is the M2 right there, which is good. So then I can simply solve that thing for M2, which is that. And actually, you can see that even better, the G's will actually cancel on the top and the bottom. And then you can just have D1 M1 divided by D2. Using your calculator, you can find that the mass is 4.98 kilograms. Which is fine, that makes sense. M1 is much larger than that at 15 kilograms, but it is also much closer to the point of rotation. M2 can be bigger, M2 can be smaller than M1 because it's so much further away, and so the torque is going to be larger from a smaller mass because the arm here, the distance from the point of rotation, is bigger. But of course, the torque on this side has to be the same as the torque on this side. Okay, looks like I filled up the page, so if I'm going to go to part B, I better get a new page going. All right, so there's a screenshot of the work I did on the last page. Importantly, I still have my free body diagram and the forces, and then just let's remember that the mass calculated out to be 4.98. So now we want to figure out what the force is on the balance point acting on the board with, and so that's going to be this force right here, that thing that we set the pivot point to be 0 so that we wouldn't have to deal with that. Well, now we actually want to deal with it. We want to find out what it is. But looking at the y direction, it's easy to use the y direction to find the pivot force because now we've calculated what M2 is. So we can pretty simply just rearrange that to be FP, M1G plus M2G. And now since we know what M2 is, we can simply calculate what FP is, and the answer ends up being 196 newtons. So it's relatively easy to do that after you find the additional forces and the conditions using the torque formula. It's easy to go back and use Newton's second law in a linear fashion to find the pivot force that's acting at the center of this beam. Okay, so this has been a solution to the seesaw whiteboard problem. It's a relatively easy application of these ideas, but it does have the full two steps in it. One of which you have to use the torque formula by setting the pivot force equal to 0 by picking the pivot to be the origin. And then the second part is to find that pivot force afterwards using Newton's second law. Okay, great. I hope this has been helpful. Thank you for watching, and I will see you guys next time.